Hi everyone, I'm Yu Jiajing. Today I'll be introducing our recent work on a near-optimal method for minimizing the maximum of n convex losses. This is joint work with Hilal Assi, Yair Karman, Aaron Jabalabadi, and Aaron Sidford. We study the problem of minimizing over x, maximizing over n functions fi, where each function's fi is convex, Lipschitz, and non-smooth. This is a max-structured objective induced by a max operator. Another such well-known structured convex objective is the finite sum structure, which is minimizing the average of n convex losses. Both are typical structure preserving convexity and find great usage in practice. For our max structure objective, when functions fi are linear, it models hard margin SVM in machine learning. Further, when fi's are general convex losses, it is a prevalent objective for robust optimization, adversarial learning, and distributionally robust optimization. For this problem, we ask the question of what is the necessary and sufficient oracle complexity for solving it when nd is way larger than 1 over epsilon. We focus on first-order oracles, which returns the function value and gradient of a given point x as the index function fi. We use n to denote the number of losses, d as problem dimension, and epsilon as accuracy. This regime is the typical big data low accuracy regime where first-order methods are of interest. First of all, we situate our main results in literature. For the average loss problem in this setting, a matching lower bound and upper bound of epsilon to the -2 is well known. On the contrary, the knowledge on max loss problem is much more limited. It is in our recent work that a formal lower bound of n times epsilon to the -2/3 plus epsilon to the -2 is proven. This leads to a huge gap with the classical upper bound of n times epsilon to the -2 achieved by subgradient method. We improved that upper bound to a better complexity in prior work. In this work, we finally obtain a new algorithm with nearly matching upper bound. This closes the gap for non-smooth loss functions fi and show a concrete regime where max is no harder than average. Our approach is based on the following 4 steps. We first approximate the max objective by global softmax. Then we implement a ball regularized optimization oracle for such softmax objective using SGD and rejection sampling. We plug in such implementation to a generic acceleration framework using BROO oracles. And lastly, we show that the accuracy required for subproblem implementation can be reduced using the idea of multi-level Monte Carlo. We are able to generate further improvement compared with prior work using 2 key techniques. First, we use rejection sampling, which allows us to sample exactly with low cost from an ever-changing distribution. Second, we use an unbiased low variance estimator for solving subproblem, which reduces the typical higher accuracy required. Now we explain these 2 ideas in a bit more detail. In order to be able to estimate the gradient of softmax, we need to sample from pix, which is changing after each iteration. To do that, we observe the nice stability of softmax. When restricting x on an epsilon ball, the function's value fi will be additively close. Consequently, the probabilities pi will be multiplicatively close with one another as well. Thus, to sample from pix, we first sample from pix bar and then correct the arrow by only accepting it with probability pix over pix bar. Note that for the first step, it only takes OM pre-processing queries. For the second step, it only takes constant queries in expectation due to this constant accepting probability. Altogether, this gives a cheap cost sampler as we need. The second idea is instead of solving subproblem to high accuracy, it suffices to find an unbiased estimator for the problem with low bias and moderate variance. Consider a strong convex objective with access to its bounded stochastic gradient. We can build an unbiased estimator of optimal solution using geometrically decreasing iterates of SGD-type algorithms, building on the idea of multi-level Monte Carlo. Compared with standard SGD-type method, such estimates allow us to find a same delta bias solution in constant queries in expectation instead of 1 over mu square delta square queries by only incurring an extra moderate variance. Such an idea also serves as a new primitive in stochastic convex optimization and find more utility for randomly smoothing non-smooth objectives and other acceleration frameworks. Please feel free to check out our extended abstract for more details. Thank you very much for your attention.